All right, so today we're going to take a look first, just briefly, at what calculus is, some aspects of calculus. And the first thing I'd like for you to do is I'd like for you to think about, if you've had calculus before, what you would say calculus is. If you haven't had calculus before, what you imagine it might be. So write something down. You don't have to share it out loud, although I'm going to ask if some of you will. What would you say calculus is? And I'll give you a description from my perspective in just a moment. So would somebody share what they wrote? There's really not a right or a wrong here. What do you think calculus is? Yes?
I said the cornerstone of technology because it helped a lot of computers.
That's very true. It was a cornerstone of technology, yeah. What other kinds of things do you guys have written down? Bold, somebody share. We're going to have to get over this shy. All right, I'll tell you what I would describe it as. I've had a book describe it this way before, and I really liked it. It's very broad. Mathematics can be described, or calculus can be described as the mathematics of change. It looks a lot at how things change, sometimes over time, sometimes not. And it's not just how things change in the physical sense, you know, like in engineering. Some people think of calculus as related only to engineering. We also have a class at this campus called business calculus, and so there's a mathematics of change inside of a business context as well, that you can look at calculus in respect to that. A couple of things that you have seen before talked about are tangent lines and secant lines. But the first place you saw them is not today. Where does the first time you saw things called secant lines and tangent lines? You probably saw them in trig. Before then you saw them, though. You should have seen them in geometry. But when you saw them in geometry, they were always related to a circle. Do you guys remember that? And they were related to how a line cut through a circle when you first described them. So secant lines did something like this, where they cut through a circle. And when they cut through the circle, they intersect the circle at two places, right? So there's 2 points where they cross the circle. It's the same thing, though, if we're dealing with a curve and not a circle. And that's more of what we're going to be looking at with calculus, is this idea of a secant line cutting through 2 points on a curve. But it's still the same definition, this idea of cutting through the curve. Now, a tangent line doesn't look like that, does it? So a tangent line, instead of it cutting through the curve, kind of looks like it rests on the curve. So when we looked at it in terms of a circle, you saw something that looked, let me try that one more time, something like that. So it just touched the edge of the circle. So you can imagine the beach ball with a, stick lying against it. The stick doesn't cut through the beach ball, it just touches it on the edge of the beach ball. That would be an image of a tangent line. And we can do that with a curve the same way. So that would be an image of a tangent line. It's not drawn very well. I'm not going to promise that it is. And in fact, when you drew yours might not quite look like mine even. And we probably are all a little bit off. all right? It's just the visual image that we're talking about at this point. We're going to talk more specifically about how to actually find what that would be a lot more this semester. But that's a tangent line, okay? I'm going to do two types of examples in this section of calculus and how it can be used, and these examples are going to rely heavily on you having some kind of a calculator available to you, okay? So, this is where we are. One of the examples of calculus has to do with finding the slope of a curve at a point. So you've all been driving before and you're on some kind of an incline and they talk about the gradient of the road. Colorado is where I see it anyway, where I've traveled. Well, that has to do with slope. But when we talk about slope, we usually talk about slopes of lines, right? And they're talking about a slope of something that's certainly not a line, because the road is not a line, it's curved, right? So how do they talk about slope? Well, they're talking about it very much like we're going to talk about it here. And the way that that is referenced is if you take a look back at what we drew over here about this line, the slope of the curve at this particular point would be the slope of this line. That's what we're going to be looking at, okay? And we're going to do that with an estimation technique today. And we're going to do that with this function x cubed plus 2. So here's what I'd like for you to do. Go ahead and grab your calculators out. And I really wanted to have the calculator display today. And through various reasons, it's not happening. So we're going to do without it, and you're going to do just fine with it. So grab your calculator. If you have the TI-84 version, the kind where you can plug in a function into y equals, that's where I want you to go. If you don't, you're okay, it's fine. But just, I want you to hit y equals, and I want you to type in x cubed plus 2. Okay? All right, so the first thing to notice is that we're going to estimate the slope of the curve when x equals a, and they're telling us in this case that a is 1. So we're going to estimate the curve when we have an x value of 1, right? So the first thing we need to know, though, is we need to know, well, if the x value is 1, what in the world is the y value? And you can do this one really quickly in your head. What is y when x is 1? It's 3. Okay? So this point on my curve is the point 1, 3. Everybody good so far? Just plugged in the number 1, algebra. Now, if you've got this in your calculator, what you're going to be using your calculator for next, if you've got the TI-84s, is you're going to use the table feature. So, show of hands, who knows how to use the table feature in that TI-84 version? Okay, those of you who know how to use it, excellent. If you don't, then look on your neighbor if you have one of these calculators and see how to do it. The first thing I want you to make sure is that your table's set up correctly. So, I want you to hit second window. When you hit second window, it should give you some features at the bottom where it says auto ask, auto ask. Does everybody see that who has one of these calculators? The first place where it says auto ask, I want you to highlight the word ask. Is everybody tracking with me who has one of these? If you don't have one with you today, you have one later and you need to help for me to get that set up, just come see me in my office and we'll get it set up. It won't take very long.
For the independent?
Yes, for the independent. The very first one, the independent one, needs to be on ask. Okay, next thing you want to hit is I want you to hit second graph, and that takes you into a table that should now be blank. Is your table blank? Okay. Now, if you already put in tangent x, when you put y equals, you put in tangent x. If you did that, you should have an x column and a y column. Does it say x and y on top? Okay, then you're in the wrong mode. That's okay. Hit mode. And go down to change it to function. There should be a place where you're in polar or parametric. Change it to function. Does everybody else have an X and a Y as those column headers? Okay, great. What you can now do is you can enter in any X value you want and it will automatically spit out a Y value for you. This saves you keystrokes. Okay, that's really all it does. There's nothing special really about it. It just saves you some time. So if you have a scientific calculator with you, you're going to have a few more keystrokes on this particular part of our exercise. But that's okay, you'll be fine. Everybody good so far? Now, let's talk about what kind of values we were interested in. What we're wanting to find is we're wanting to find the slope of something. How do I find slope? Okay, y equals mx plus b is a slope-intercept form of a line, but it doesn't find the slope.
Oh, isn't it like y2 or y1 on
All right, so that is one of the formulas for it, yes. So m equals y2 minus y1 over x2 minus x1. And it would be perfectly acceptable if you wanted to have the subscript 1s listed first and the subscript 2s listed second. They just need to be in the same order. Okay, so as long as we put the subscript 2s in the same spot, we can put them in either of the spots. There's other ways you've heard this described. How else have you heard slope described? Rise over run. That's it. Yeah, that's one. Anybody else heard a different one? Maybe delta y over delta x. Delta means change in. Sometimes you hear it described that way too. So this is how we find slope. So notice, what do I need in order to find the slope?
You need 2 points.
I need 2 points. And right now I have 1. I have the point 1, 3. And I'm going to use the point 1, 3 for all of my calculations, but I need to somehow have another point. Does that make sense? So what we're going to do is we're going to get another point. And we want the other point to be close to the point 1, 3. Everybody good so far? So if you take a look back at this dirty image, what we're actually doing is something like this secant line. We're just making sure that these 2 points that we're using are really close together. Because if they're really close together, it starts to look like the tangent line instead. Does everybody follow me on that? Okay. All right, so taking a look at this value, there's nothing special about the values I'm about to pick, except that they're going to get closer and closer to the value that I want. So the first value I'm going to pick is I'm going to pick 1.1, because that's awfully close to 1, right? And then I need to pick another value getting a little bit closer to 1, and so I'm going to pick 1.01. What do you think I might pick next?
2.001.
That is exactly what I'm going to pick, 1.001. And again, there's nothing special about these points. They just get ever increasingly closer to the point 1. But they're getting closer to the point 1 from values that are slightly larger than 1, aren't they? I mean, all those numbers I picked were slightly bigger than 1. I want to do it from numbers that are also slightly smaller than 1. That's kind of why I have these 2 tables set up, is to kind of compare them from both sides of the number 1. So the other values that I'm going to pick, I'm going to start with 0.9. My next point I'm going to do is 0.99. What do you think I might do for the third one? Yeah, again, there's nothing special about these points, but they're kind of easy to just decide on. And they get ever increasingly closer to the number 1. And there's really nothing special about the fact that I did 3 of them. I could have done 4 or 5. But 3 is going to be enough for you to see what's happening, so we just are going to do 3. Okay? All right, again, I need a point. I need an x value and a y value in order to find slope. And right now I've picked a bunch of x values that I can use and I can find some slopes with, but I can't find them yet unless I have the y values. That's what your calculator is going to let you do. So if you've got a scientific calculator, you're just going to plug these in one at a time into this equation. If you have one of the graphing calculators where we set up the table, you can flat out just plug these numbers into your table and it will automatically spit out the y value for you in the other column. It's kind of handy. All right, so go ahead and figure some of those through, and we're going to fill them in, and then we're going to do the slopes together. All right, so somebody tell me what you got for that y value when x was 1.1, that first blank. 3.331. Good, and that actually stopped at the value 1, didn't it? There wasn't anything after, yeah. How about when you put in 1.01? Good. And your calculator actually stopped probably at that 3. There are more values after that. Some of you who are scientific calculators and are spitting it out, it's going to keep going further. As long as you write me down 4 decimals, I'm going to be good with that. Sometimes your book will use 4, sometimes it'll use 6. As long as I can see 4 decimals, we'll be okay. How about the third one? Yep, and then it actually goes 0, 0, 3 if we went going further, so I'm going to put a 0 in that spot just so that we recognize it does keep going. All right, let's do the other side. The f of x is for the 0.9 ones that we have. We'll come back to the slope in a sec. What is the y value when x is 0.9? 729? Okay. How about 0.99? Excellent. And how about 0.999? 997? And it must have a 0 or something after you go that. Okay. All right, so we're going to use your calculator then to find all of these slopes. I'm going to set up one of them, and then all of the rest will set up the same way. As you're doing this, keep in mind that it matters that y goes on top, and it matters that the order is the same. I'm going to use this point up here, the original one that we started with, as x1, y1, which means in all of my calculations, I'm going to have a -3 on top and the -1 on bottom. You don't have to do it that way. You could do it the other direction. It would be fine, but that's the one I picked. Okay? So for the first one, as I do this, I would be putting in 3.331 minus the 3, and then the 1.1 minus the 1. Couple of things in your calculator as you're doing this. If your calculator has parentheses, make sure you put the entire numerator in parentheses, and then you do the division and the entire denominator in parentheses. Otherwise, it's going to divide things not the way you wanted it to. If you have a TI-84, once you enter this into your calculator one time, you can actually use the second enter feature, which will pull up the previous line you did, and you can make changes to it. Okay? If you're not familiar with that feature and you want me to show it to you once we get finished with class today, just ask me and I'll show you so that you can make sure and see that feature, because it's really nice. Okay, so what do we get for the slope on the first one? All right, it's 3.31. Did we get a slope for the second one yet? 3.03. Okay, how about the third one? It should have more decimals after that. If you're working inside of your calculator, make sure that it's showing you enough decimals in your answer to actually see that it's something else. Did anybody get any decimal points after that? I've got 003 written down. Is that? Let me see what you've got. Oh, that's because you're using a value up here that had only the 4 decimal places. It's okay, not to worry. All right, how about on the other half of this graph, or this table? How about that 0.9 one, that very first one? What do you have? 2.71. What's your next slope? Good. And how about the last one? Yeah. So the reason it's giving some of you 3, as I was looking, remind me your name? As I was looking at Carrie's paper, is because when we're using this, we actually used only 3 decimals right here. If we had used, it goes 003 next. If you had used more of these numbers, I'm sorry, over here, 3.003, and it would go 003. If you used a 6 decimals here, we'd actually get it to be a little bit more accurate. I'm not terribly concerned about it, because the whole point is for you to notice what happens as you move down these tables in the slope column. What value do both of those slopes get close to? 3. And in fact, they're getting so close that some of your calculators, when we rounded things off a little too early, are actually telling you it is 3, aren't they? So what we're going to actually say is that the slope, and we're going to use an approximately because we didn't prove anything. We used a numerical sort of getting closer approach to approximate what's going on. Now, the reality is that it is the slope. It is correct. It is 3. But we didn't really prove that. We just approximated that to be the case. Do you guys see the difference here? Okay, so we're going to say it's approximately 3. Okay, is that good? All right, we're going to do one that's a little bit trickier now, simply because it has what in it? Tangent. And what makes tangent a little bit trickier? What is it? There's asymptotes. Yeah, if we had any asymptote issues, we're not going to have any asymptote issues with this one, but that definitely can cause concerns. What else makes tangent a little trickier? Or what makes this particular problem with tangent a little trickier? Yeah, it has a fraction. Not only is it a fraction, but it's in radians. It's an irrational fraction, right? I mean, like it's a pi. That makes it a little trickier. Like, the reason it makes it trickier is because you see on the last problem, my a value was a whole number, wasn't it? Yeah, so it was kind of easy to say, oh, my a value is 1, and I can get a little bit bigger than 1, a little bit smaller than 1, and that's really convenient because I'm dealing with a number 1. It's a whole number. Pi over 4, you're not so convenient. Okay, so we're going to first start with this. I'd like for you calculator, and I'd like for you to get a decimal approximation for pi over 4 because that approximation is going to help us put the x values in. Okay? All right, so approximately. So if you put in your calculator and you put in pi over 4, I would like for you to give me an expression. Let's go to 6 decimal places just so that it's easier for us to identify some numbers as we work. What do you get?
0.7853. How many? 6?
Okay, just a second. Say that again for me, 7.8.
785398.
9.8, okay. And then there's more stuff after that, right? It keeps
Yes.
going. All right, so we've got this approximation. So we're roughly at about 0.785, right? Fairly close. Now what happens if we were to take the value pi over 4 and we plug it into tangent? Do you remember what the tangent of pi over 4 is? It's 1. So the ordered pair when we do the slope here in a minute that we're working with is the x value of pi over 4, and we do need the x value pi over 4. Don't approximate that there. And then the y value of 1. So when we're calculating slope, that's going to be my x-y pair that I'm using, just like I used 1, 3 last time. But I'm going to think about that number 0.785 so that I can figure out x values on either side that are close and getting closer. So I'm going to start with something a little bit bigger, and I'm going to choose 0.8. There's nothing special about 0.8, but it's close to 0.785 and a little bit bigger. Make sense? All right, so again, there's nothing special about these numbers, so somebody else pick me another number after 0.8. Something that's slightly bigger than 0.785398, but it is smaller than 0.8.
0.81.
That's bigger than 0.8. We want something slightly smaller. 7.9 would be okay.
0.799.
That's bigger than 7.9.
Oh.
7 would be smaller than the 7.85.
2.78.
How about 7.86? I think that one will be nice. That'll work. So remember, our goal is to pick numbers that are, in this first column anyway, the one I'm working with, is bigger than the 0.785398. But as I go down the table, they get closer to the number I'm wanting. So visually, what you should sort of be picturing on your graph is you start out with these 2 points here and here, right? 2 points kind of far away if you zoomed in close enough. And as you get closer together, those 2 points get closer together as well. So we're picking points that get closer to the point that we're concerned about to find the slope for it. All right, so we'll figure these in just a second. Let's do the same thing on the smaller than values. Now, the smaller than values are kind of cool because we can kind of cheat. So let me show you. I'm going to pick 0.7. And then I'm going to pick 0.78, and then I'm going to pick 0.785. Does that feel like cheating a little bit? It kind of does, right? I mean, I'm just using the actual values themselves, because if I pick 0.7, for instance, that's essentially like turning everything after that into zeros. That's smaller. But then if I pick 0.78, I'm closer than I was before, and then turning everything else into zeros, so I'm still smaller. And then the 785 for the same reason. Okay? If you picked different numbers, but it still had the effect that you were getting closer to the one you were concerned about, it'd still be okay. It would still be right. All right? So as you're looking in the back, if you see a table and your table doesn't match yours exactly, it doesn't mean your table's wrong. I mean, your table still could be wrong, but that doesn't mean it is. All right? If you're using your calculator then in that table view, you can still get those f of x values really quickly. Let's go ahead and keep those f of x values to the 4 decimal places at least. If you want to err on the side of safety, you can put 5 or 6 down. That would be fine. As we saw last time, things kind of got a little bit funky when we simplified it to 4 decimals. I have actually 6 decimals down on the paper when I was writing mine, but I'm going to be okay with 4. What do you get when you put in 0.8?
0.
Okay, hang on, let me start again. Tell me one more time.
0.0140.
For the f of x,
I got 1.0296.
1.0296.
Yeah.
Okay, so let me pause for a moment and make sure. Is everybody in radian mode?
Um,
Yeah, I know.
yes,
You're
I
never going to need to be in degree mode again in class. So make sure you're in radians, okay? And then try again.
Is there a way to clear all of like the x values before you start, or do you just have to like go back?
Yeah,
and-
there
right,
is.
okay.
I can remember. You can delete them one at a time, or I think you can go up on top of the. No, you can't. You just have to delete one at a time. There's
Okay.
another list where you can clear them all out at once, but it's a different list. Okay, so is everybody good with the 1.0296? All right, what do you get for the 0.79?
1.0092.
Okay, and how about 0.786?
1.0012.
Okay, is that good for everybody? Pretty close anyway, what you have? All right, let's do the other table. What happens when you put in the 0.7?
0.84229.
Okay, how about 0.78?
98926. 1.98926.
Okay, so you're giving me 5 decimals, that's fine. 26, no, it's fine. I'll go with your 5, it's good. And how about that 0.785? 99 what?
92, sorry.
Three nines or 1
Yes,
9?
3 nines.
Okay. Are we good with that? Okay, so at least 4 decimals in each of those, that's good. So we're going to calculate that slope like we did on the previous problem. So we have y2 minus y1 over x2 minus x1. Now as we calculate this slope, I'm going to put then in the values at the end, minus 1 and minus pi fourths. And please use the pi fourths. I've had 2 students from my other section already come in with questions about that. They were not using pi over 4, they were using 0.785 as a round off version of pi over 4. And their answers kept coming out funny. And it took me a while to figure out why their answers were coming out funny, and it's because they were using that rounded pi over 4 version. So your calculator will tolerate pi over 4 just fine. Let it. Okay? So one at a time you can go through these. So the first one would look like 1.0296 minus the 1, and then on the bottom 0.79 minus pi fourths. Oh, I'm sorry. I was already on the left second line. You're right. The first one would be 0.8 minus the pi fourths. Thank you.
Now, if you just do it, just write in like pi over 4 like that, it'll be okay, because it'll do the.
It'll do the division properly. The only concern that you need to be aware of is to keep the parentheses around the numerator and the parentheses around the denominator.
4 decimal points.
Yeah, 4 decimal points is good. Do we have the first one?
2.0271.
Does somebody have the second one?
1.999.
How about the third one? Does everybody have that value for the second one? Okay.
1.9939.
All right. I think the numbers are doing funny things because we rounded to 4 decimal points on the f of x, but it's okay. We'll tolerate it for now. How about the other side of the slope? That 0.7 value in there.
1.8468.
How about the next one? How about that last one? Okay. We're getting some funny rounding things going on because we've rounded off our stuff so closely with just the 4 decimals or the 5 decimals. If we had the 6 decimals, we would see it a little bit more clearly. But what is this approximately equal to on these slopes? What's it look like? It is, and it actually really is 2. And the more accurate we are, the more decimals we keep, the closer that it actually be. We should actually be seeing, going down these lists on the slope, the values getting closer and closer to 2, and we're really not quite seeing that, to be honest. We've got some error in our rounding going on. But regardless, we still see a slope that's approximately 2 in all the cases, right? We're getting close to the number 2. All right, there's one other example that I want us to take a look at. And this example is finding a length of a curve. So imagine taking a piece of string and lying it along the graph, and then picking up that piece of string on the edges and then measuring it. Okay? So that's what we're actually going to be doing, but without actually taking it and measuring it. We're going to be doing it using calculus. So this one is to estimate the length of the curve of y equals f of x on the given interval using n equal 4 and then n equal to 8 line segments. So n equal to 4 means that we're taking the piece and we're cutting it into 4 pieces. Right? So you're taking the string anyway and cutting it into 4 pieces and measuring each of the 4 pieces of string. And then when we do it for n equal to 8, we're going to measure each of the 8 pieces of string and we're going to add them up. So everybody sort of have a picture of what's going on. Okay? All right, so to start with, we have the interval from 0 to 3. So if we were to take the interval from 0 to 3, the first end point is the end point 0, and the last end point is the end point 3. So if you imagine starting at 0 and ending at 3, and you cut it in half, where would you end up being if you cut it in half? 1.5. So this dark gray one in the middle that I've got on the screen is 1.5. Now if you took that 1.5 and back to 0 and you cut that in half, where would you be? 0.75 actually on this one. Yeah, 0.75, right? The other half, if you go between 1.5, and 3, where are you? 2.25. Now, if you're not in your mind readily thinking about these numbers, or if they were really messy and you were sure like, oh, well, I can't split that in half very easily, the way you split things in half is you add the 2 numbers together and divide by 2. All right, so if you wanted to split 1.5 and 3 in half, you can add 1.5 plus 3 and then divide that number by 2, and that's the halfway point. That's how you get the midpoint of something. So these are the x values, okay? You guys are already very proficient at using your calculator to do this. So you're going to take each one of those x values, and you're going to plug it into the function f of x equals square root of x plus 1, and you're going to find the corresponding output y value. Okay? And so that we can keep my accuracy, I'm going to go ahead and have us write down 6 decimal places. In the table you're using, sometimes it doesn't look like there are 6 decimal places, but if you highlight, that is move your cursor around till you're on top of the value, all of the decimal places will be displayed on the bottom of your screen. So you can see as many decimal places out as you want, within reason anyway. Okay? All right, let's do the easy one first. You can do this one in your head, I know. If I put in the number 0, what's the f of x value? 1. Good. All the rest of them we need a calculator for. All right, so put in f of x, I'm sorry, x equal to 0.5. What do you get for f of x? 0.75, excuse me, I think I said 0.5. 0.75.
6.
Does that look good, you guys? Great. Let's put in 1.5.
1.58, 139.
581139.
Yes.
Okay. How about 2.25?
1.802776.
Excellent. If you put in the number 3, you can actually do that one in your head as well. What do you get? 2. All right, now, we're not calculating slope on this problem, right? This problem has nothing to do with slope. It has to do with distance. Does anybody remember the distance formula? What do you remember? I'm like pulling out all sorts of stuff you don't remember, right?
Negative b, I know that's wrong.
That's the quadratic formula.
That's true.
Does anybody remember it? We're on the right track. The square root of,
Oh, yeah.
well, that's one way to think about it. You guys remember the Pythagorean theorem? A squared plus b squared equals c squared. The distance formula is a application of the Pythagorean theorem. But you would remember it looking probably something like this. That looks familiar now, right? All you're really doing is you're taking the difference in the x values and you're squaring them. The difference in the y values and you're squaring it. And then you add those and take the square root. That's what that formula says. Now, the beauty of this formula is that when you square things, what happens? It makes them all positive. So it actually doesn't even matter if you subtract things in the right order in this formula. That's really nice. It'll save you some keystrokes if you keep that in mind as you're working, because you can actually put the subtraction in either order and it'll work. All right, so taking a look at this, we'll fill in the first one together. Notice on this that when we're doing the difference in the x values, each of these x values, how far are they away from each other? They're all 0.75 away from each other, aren't they? So this piece of the formula right here is never going to change. It's always going to be 0.75 squared. Isn't it? So that's kind of nice because we won't have to change that as we're working through this. So part of my formula is simply going to be 0.75 squared. The other part's going to change each time because the y values are not equally distanced. So the first one, for instance, that I'll do is I'll do the second y value, which is 1.322876 minus 1. And your calculator, again, will let you enter this in there just like that. Put a big old giant square root and it'll open a parenthesis. If it doesn't, you need to. You can type in 0.75 squared minus, open another parenthesis. Type in the second piece here, that's the 1.322876 minus 1. Close the parenthesis, square it, and then you can close the whole parenthesis for the square root part after that. If you don't close the whole thing, it won't complain either, so it doesn't matter. Now, there's nothing to fill in on the first place right here because there is no previous point to compare that to. So our first place we're actually going to fill in a piece of information is in the second box of that column. What is it? What's the difference in those squared? And sorry, I've got an error on that. That's a plus sign right there. I'm sorry. Please make sure your calculator reflects that plus sign. That's what I have too. 0.816547. And if your last decimal's off, it's okay. For rounding purposes, it doesn't matter at the last point. Round up, round down, round off, I don't care. Does that make sense? Did everybody get that value when you put it in? All right, so as we go to the next value, what needs to change here in this formula? Well, I actually don't need this number 1, do I? What number do I need instead? Right, I need that 1.581139. And again, because the subtraction order doesn't matter, I can simply replace that 1 with that 1.5. Is it technically in the wrong order? Well, yeah, okay, it is. Does it matter? It doesn't, because the subtraction and then squared is going to give me the same thing regardless. All right, so let's fill in this one right here. What do you get?
793,221.
That's what I have as well. All right, so here's what I would like for us to do, okay? I would like for you guys to finish filling in these 2 little spots on this table. All right? And then that's all I want you to do before Thursday. Can you do that? That's minimal homework, right? 2 little spots on a table, okay? And then on Thursday, we will finish this other table right here together. This table right here does it with 8 line segments. We will go through this quickly, though, so that we can move on and get into the next lessons. All right?